Hello and welcome to my channel. In this video, we will learn about quicksort, also known as partition exchange sort. This is one of the fastest sorting algorithm. After merge sort, it is another example of divide and conquer approach to problem solving. The quicksort method sorts a list by selecting a pivot value. In this image, the last element is selected as the pivot. To sort in ascending order, the list is partitioned so that the values lower than the pivot are moved to its left and the values larger than the pivot are moved to its right side. This creates two partitions and the process is repeated on smaller and smaller partitions until the list is fully sorted. There are various methods of selecting the pivot element. Remember that the algorithm selects a new value as the pivot using the same rule each time the list is partitioned. So if you are implementing a quicksort algorithm, you will need to do some modeling with realistic data in order to make the best choice. So here are the steps to code quicksort algorithm. This is the given array, and in this video I'll be implementing quicksort algorithm by choosing the last element as pivot. So the first step will be selecting the pivot element. Next, we are going to partition the array around the pivot element. We move all the elements smaller than the pivot to its left side and the elements greater than the pivot will be moved to its right side. After this task, the pivot element will be in its correct position, and now we will be executing step 1 and 2 recursively on the left partition to sort the elements as per the quicksort algorithm. Once the left partition is sorted, we will sort the right partition, and the call to recursive function is stopped when the base case is reached. The base case is an array of size 0 or 1. So here is the C++ code for quicksort algorithm. Here we will be defining two functions. One is quicksort. This function is recursive as it invokes itself. You can see these two function calls here. The function accepts three arguments: variable ARR, variable start and end. On the basis of this condition written here, we will be performing these three tasks. So now let's examine the execution of this quicksort function. So this is the code of quicksort that we will execute here step by step. This is my array ARR. Here I'm going to maintain a stack in which I'm going to store the values of start, end and PIV index every time I make a recursive call to the function quicksort. So let's begin. The function here quicksort accepts three arguments: the variable ARR, the value of start, which is the index of the first element, and the end variable, which is 6, the index of the last element. So inside the function we have this condition: 0 less than 6. The condition here becomes true and we call the partition function. So this partition function will bring the pivot at its correct place and also brings all the elements smaller than the pivot on its left and the larger elements will be on its right side. So let's store the values of start and end in the stack and make a call to the partition function. We pass the array, the value of start and end to the partition function. Let's execute the partition function and see how it is going to work. So this is the array that we have received. This is my variable ARR. Start value is 0 and end is 6. So the first statement inside the function you can see here is setting the pivot element. As during our algorithm, we will be considering the last element as a pivot. So here 5 is the pivot element. So we set the value of a pivot variable, which is ARR of n, and it is 5. Here I maintained a variable I and we will see its use in the further statements. We will initialize I with the value start minus 1. So start is 0. So I will get the value minus 1. J is the loop counter which is initialized with the value of start, which is 0. This J loop will run from 0 to end minus 1. The value of end here is 6. So 6 minus 1, it is going to run from 0 to 5. Inside the loop, we will compare the value at jth index with the pivot element. So first we compare ARR of 0. Now ARR of 0 that we can see here is 10. So 10 less than 5, condition becomes false, and we move to the next iteration of j and we compare ARR of 1, that is 15 less than 5. This is also false and we have the value of j as 2. ARR of 2 we can see in the array is 1. 1 less than 5 condition becomes true. Now this step is needed so that we can bring all the elements smaller than the pivot on its left side. So first we increment the value of I, making it 0, and we are going to swap ARR of 0, which is 10, and ARR of 2, which is 1. And after this step my array will become 1, 15, 10, 2, 6, 12 and 5. Next we have the value of j as 3 and we compare ARR of 3. ARR of 3 is 2. 2 less than 5 condition is also true. So we are going to increment the value of I. We make it 1 and we will swap the values at indices 1 and 3. So this is index 1 and this is 3. And after this step my array will be containing these set of elements. So these are the changes that I've made in the array. And then we have the next value of j as 4. We compare ARR of 4. ARR of 4 is 6. 6 less than 5 condition is false. Then we have ARR of 5. Here we compare 12. 12 less than 5 condition is also false. And the value of j becomes 6. Now this will exit the loop and we will reach this statement. Here we are going to swap the values at index I plus 1. So the value of I is 1. So it will be 2 and ARR of 6. This is done to bring the pivot at its correct place. So as we can see, we have elements smaller than 5 here. So this becomes the correct place for pivot. And after this, the array will be containing these elements. And last, we return the value I plus 1. So the value of I we have seen is 1 and we will be returning 2. Going back to the quicksort function, so here is the updated array and now we will be executing this statement where the quicksort function calls itself for the first time. So here I call quicksort, giving it the arguments ARR. The value of start will be 0 and the value here PIV index minus 1 will be received in the variable end. So it is 2 minus 1 which is 1. Now I'll also update these values in the stack. So now we are going to check the condition here once we enter inside the function. So value of start is 0 and value of end is 1. This condition 0 less than 1 here becomes a true and now we call the partition function. This quicksort function call is for the elements on the left side of the pivot. So this was the pivot element in the previous function call and these two elements which were on the left side of the pivot, we will be working on these elements here in this function call. So now as the condition becomes true, we invoke the partition function. So we write this function call here. So here in the arguments we are going to pass the array, the value of start which is 0 and the value of end is 1. Let's go to partition function. Now here the value of start is 0 and end is 1. This is my array. We will set the pivot element as we are considering only this partition. So here this will be the last element and will become the pivot element. So pivot is ARR of end and the value of end we can see here is 1. So ARR of 1 which is 2 will become the pivot element. Here I maintain variable I and it will be initialized with -1, start -1. And this is my variable j, the loop counter initialized with 0. Now j here will run from 0 to n minus 1. The value of n that we have is 1. So 1 minus 1, that means j will run only once. Now here we are going to compare if ARR of 0. Now ARR of 0 that we can see here is 1. So we will be comparing 1 with the pivot element which is 2. The condition here becomes true. We increment the value of I, making it 0 and we are swapping ARR of 0 with itself. So as per the latest standards, this swap function will swap the values only when they are at different addresses. So there will be no change in the array. And now j increments to 1. And you can see that the loop will stop and we will move to this statement here. Here we are swapping the values at ARR of I plus 1, which is 1, and ARR of n, which is also 1. So again, there will be no change in the array as we are just swapping 2 with itself. And now in the end, we are going to return I plus 1, which is 0 plus 1. That means 1. So 1 here is the index of the pivot element, which is 2. So let's take back this value to the quicksort function. So the PIV index that we have got from partition function is 1. Let's put that in the stack here. And now we will be executing this statement. So let's invoke a quicksort. Here we are going to pass the array. There is no change in the array. And the value of start, which is 0. PIV index minus 1. So 1 minus 1 will be 0. From this place, again we are going to invoke the quicksort function. Here this line. So 0 becomes the value of start and this 0 becomes the value of end. Let's put that value in the stack. So here the value of start, this is the value of end. And now we are going to compare the values for this condition. Start less than n, 0 less than 0. Condition here becomes false. So I'm not making any tree-like structure here because this function has now stopped, and therefore I am going to remove these values from the stack as the call to recursive function here gets over. So after this, we are going to move to this line where we call the quicksort function here for the elements on the right side of the pivot. So now we have quicksort for the right side values. Now we are talking about this partition, and as we can see here that 2 was considered as the pivot element, and obviously there are no elements on the right side of this pivot element in the first partition. So we are going to work on this partition and let's see how the last function call here will work. So we pass array, we pass the value PIV index plus 1. So in the last function call, the value of PIV index was 1. So 1 plus 1 will be 2. And we pass the value of n, which was here 1. Now when the quicksort calls itself, it goes to this statement where this becomes the value of start, this is the value of end, and we are going to check for these values. Now again I am going to put these values in the stack, and as per the condition written inside the function start less than n, so we compare these values. 2 less than 1 condition becomes false, and therefore this part of the stack also gets omitted, and we are finally over with the partition on the left hand side, which was containing the values 1 and 2, and therefore the second function call, which was recursive, and you can see it's working here, is now over. And now we are going to work on the elements which were greater than the pivot, which was 5, which is the right partition. So let's see how it is going to work. This state will also be removed from the stack as we are done for the left partition of the array. And now we are going to move further, working on these set of elements. So here I invoke quicksort. We pass array, ARR, the value PIV index plus 1. In the last state of stack that we can see here is containing the PIV index value as 2. So we are passing 2 plus 1, which is 3, and the value of n we can see here is 6. So this statement goes to this part where the function is calling itself, and the value of start that we get is 3. The value of end here is 6. Now we are going to check if 3 is less than 6, condition becomes true. And now again we will create those 3 lines, a tree-like structure, to understand this quicksort recursive call. Now we call the partition function. We pass array, the value of start and the value of end. Let's go to partition function. So now as we are working on this partition, this will be considered as the pivot element. The value of start that we've got is 3 and end is 6. So we set the pivot element ARR of n, which is 10. We have a variable I, setting it as a start minus 1, that means 2, and this is our loop counter. Now j loop runs from 3 to end minus 1. The value of n that we have is 6, so it's going to run from 3 to 5. We compare ARR of 3 with the pivot element. ARR of 3 that we have is 15. 15 less than 10 condition becomes false. And here we are on the next iteration of j. ARR of 4. ARR of 4 is 6. 6 less than 10, condition becomes true. Similar to the left partition that we did earlier for these elements 1 and 2, we are again going to bring the element smaller than the pivot on its left side. So here I increment the value of I, which is 3, and I'm going to swap ARR of 3 and ARR of 4, that is the value of j, and my array will be now containing these values. Now we have the next iteration of j, which is 5, and I compare ARR of 5. ARR of 5 that we have is 12. 12 less than 10, condition becomes false, so there will be no change in the array. And now you can see that we are now out of the loop, and we move to this statement where we are going to swap ARR of I plus 1, that means ARR of 4, and ARR of n, which is 5. So here we are going to swap 15 and 10, and my array will be now 1, 2, 5, 6, 10, 12 and 15. And now we return I plus 1. The value of I that we have is 3. So we are going to return 4 to the quicksort function. Here PIV index that we have got is 4. I'll mark it in the stack. And once this is done, we move to this statement, which is going to work for the elements on the left side of the pivot. So this is my updated stack, and this was the pivot in the last state. This one element is on the left side of the pivot, and 12 and 15 are on its right side. So we are going to work for this, and now we invoke the quicksort function. We pass array, we pass the value of start. So start here is 3, and we pass PIV index minus 1. So PIV index that we have is 4. 4 minus 1 is 3. So do remember that we are going to make this recursive call only when we have elements more than 1. So here 3 less than 3 condition, you can see here, becomes false. So there will be no working for the left side of the partition, as we have only just one element, which is 6. So we are out of this part now, and now we are going to make a recursive call to this function. To this function we pass array, we pass PIV index plus 1. So PIV index that we have is 4. 4 plus 1 is 5, and the value of n we have is 6. Now here we invoke the function and we execute this condition. 5 less than 6 condition becomes true. So now again we are going to work on this recursive call where we execute these 3 statements. Let's see how it works. So we execute the partition function as the condition is true. This partition function gets array, the value of start, which is 5, and the value of n, which is 6. Let's go to partition function. So this is the array here because we are working on this partition. So the last element becomes the pivot element, and the value of start that I've got here is 5. The value of end here is 6. So now we are going to set a pivot. ARR of n that we have is 15. We start with variable I, making it start minus 1, which is 4, and the loop counter initialized with 5. So j will run now from 5 to end minus 1. that means 5 to 5 only once. So here we are going to compare ARR of 5, which is 12, less than 15. This is the value 12. The condition here becomes true. So just like the previous step that we have seen, that we are going to swap 12 with itself. So here we are incrementing the value of I, and we swap ARR of I, which is 5, and ARR of j, which is also 5. So there will be no change in the array. And next, the value of j gets incremented to 6, and we exit the loop. And then we are going to execute this statement. Here we are swapping ARR of I plus 1, that means ARR of 6, and ARR of n, which is also ARR of 6. There will be no change in the array. And now we are returning I plus 1, that means we are now returning value 6 to the quicksort function. So the value of PIV index that we get is 6. Here I am also updating the stack that I had. So it was 5, 6, and the PIV index is 6. Now after the partition function is over, I am going to move to the second function call, which is quicksort. So here I invoke quicksort. I pass the array and the value of start, which is 5, PIV index minus 1. So PIV index that I have is 6, 6 minus 1 is 5. And then as it is a recursive call, we go to this part and we compare the values, start less than n. So we have start 5 and this is also 5. So I move out of this part and this again is false. This is happening because again on the left side of the pivot we don't have any elements, or the size of the array on the left partition is just 1. So now we are going to move to this function call. So now I am here calling quicksort for the right side partition. I pass the array PIV index plus 1. So PIV index plus 1 will be 7 and the value of n, which is 6. We can see it here. And again we check for the condition start less than n. This condition becomes false. And now we are also over with the third function call that we had, which is for the right partition of the array, and we can see that our array is now already sorted. So one by one we will move out of all these recursive calls and the stack will get empty. Quicksort is very efficient as it sorts in the same memory space as the original data. Extra space is required to hold a copy of a pivot value, start and end values, and a temporary variable which is used whenever the elements are swapped. As the algorithm is recursive, the space complexity will depend on the recursion method, and therefore most efficiently it is O log n. Let's discuss the time complexity of quicksort algorithm. In the best case, each time the list is partitioned, it is divided neatly into two sections of equal size. This means log n nested calls will be needed before the partition size is 1 and the base case is reached. Therefore, the best case time complexity of quicksort algorithm becomes O n log n. Now, when the pivot value is in the first or the last position of the current partition, this will result in one partition with 0 elements. So, there will be one partition, and another partition will have all the remaining elements starting with n minus 1 elements. If this happens repeatedly, the next step will result in a partition with 0 elements and another partition with n minus 2 elements, and so on. And as a result of this, the time complexity in worst case is classified as O(n) square. Now the average case depends on the initial choice of pivot value and how out of order the original list is. However, it is generally agreed that in the average case, the performance will be O(n) log n. Let's see when can you use quicksort algorithm. So the first thing is when stability is not important, when the memory space is limited, when the data set or the list you want to sort is not very large. Although the worst case time complexity of this algorithm is O n square, which is going to happen very rarely, this algorithm tends to be fast and is really a very good choice. Thank you so much for watching this tutorial on one of the fastest sorting algorithm. Subscribe to my channel and stay tuned for more updates. Till then, keep working with smile.